Good morning, children. This is class 10th physics, chapter number 12, electricity. Today's topic is topic number 5. That is the factors on which resistance depends, right? And we will start with resistivity. So, children, let's go towards the learning objectives. So, children, we will be able to know the factors on which the resistance of a conductor, its value depends. We will derive here an mathematical expression for resistivity. What is resistivity? We will see that and we will see the SI unit of resistivity. And then we are going to move towards the use of substances in application on the basis of electrical resistivity. So let's start with the first, and that is, let's see the factors on which the value of resistance of a conductor depends. Now, children, we know resistance is what? It is the opposition to the flow of charge in the conductor. This opposition is due to the collision of the charge, right? We know inside the conductor, inside any metal, there are a number of free electrons. So, children, when these free electrons are moving, they collide with each other, they collide with the walls of the conductor, they collide with the atoms, right? So, because of this collision among the electron, among the between the electron and the wall of the conductor, it results into opposition, it results into resistance, right? So the first factor is resistance depends upon the length of the conductor. Suppose I am having two wires and the area is same, and one wire is this is a short wire. Suppose the length of the wire is L1, another wire is a long wire, and you can see its length is L2, right? So as in wire L2, the electron has to cover a longer distance. So more will be the number of collision between the electron and between the electron and the wall of the conductor. More number of collision, the number of collisions will be more. So as more number of collisions, the value of resistance will be more, right? And on the other hand, for the wire L2, as the length of the wire is short, the number of collisions will be less between two electrons and between the electron and the wall of the conductor. The number of electrons will be less. And as the number of number of collisions are less, the resistance of that conductor will be less, because the collisions are less, so resistance will be less, right? So resistance depends upon the length of the conductor. It is directly proportional to the length of the conductor. More is the length, more will be the number of collision, and more will be the resistance. Let's go towards the second factor. That is, it depends upon the area of cross section of the conductor. Now, suppose I give you, suppose your class strength, suppose it is of 50 students. Now, all 50 students, I put you in a very small room. Let's assume it's our school pantry, right? So you will see the school pantry is very small. And in that, if I put all 50 students there, as the area of the room is small, so the opposition offered among the students will increase. You will start pushing each other. You will start fighting with each other, because the area in which you have been put is very less, right? So the number of collisions among you will increase, right? Then I shift you from the school pantry to the auditorium of our school, such a large room. So I'm increasing to a larger area. So as I increase you to the larger area room, your collisions will decrease, and your collision decreases, the resistance offered will also become less. So same is the case over here. Suppose you are having This is one wire and this is your second wire. As you can see, the lengths of the wire is same. Both are of the same length. Both wires, let them be of length L and L. But this wire is having cross-sectional area A1 and this wire has a cross-sectional area A2. Now here in the first case, as the area is less, so the number of collisions will be more because area is less, you are going to push each other, right? And as the number of collisions are more, the resistance R value will be more, right beta? Second case, the area is more, right? Your school auditorium. So your number of collisions will decrease. You will be very separate from each other. So you will not collide with each other, right? As your collisions have decreased, your value of resistance has decreased. So here you can see if area is less, the resistance is more. And if area is more, the value of resistance is less. So the cross-sectional area and resistance, they are inversely proportional to each other. Okay. Let's see the third factor on which the value of resistance depends. Resistance, thirdly, depends upon the nature of the material, whether your material is an insulator, whether your material is a conductor, or it is an alloy. So the value of resistance, it depends upon the nature of the material, whether it is copper, it is silver, it is gold, it is rubber, it is wood, it is plastic, it is nickel, it is platinum. What is the nature of the material? It depends upon that. The final factor on which the resistance value depends is it depends upon the temperature. Let's see how. See, suppose this is your wire. I have zoomed it, and inside wire, we know there are free electrons. Now, suppose I heat this wire. So, on heating, the electrons will absorb the heat energy, and on gaining energy, what will happen? They are just going to go mad. That is, the kinetic energy will increase, and the electrons will start doing a random motion here and there. They will start hitting each other. They will start colliding with the walls of the wire, right? So they are going to absorb the heat energy and the kinetic energy will increase and they are going to perform a random motion, right? They are going to, the number of collisions will increase. And as the number of collisions will increase, the resistance of the wire will increase. So with the increase in the temperature, the resistance of the wire also increases. Now children, from the first and the second point, or rather from the first point, we can say that from the first point, we know R is proportional to L. R is directly proportional to L. So I can write R proportional to L. This is equation number 1. From the second point, we know the resistance and area of the wire, they are inversely proportional. So R is inversely proportional to 1 by A, right? This is equation number 1 and this is equation number 2. If I combine these two equations, can I write R is proportional to L by A? Can I write this equation? R is proportional to L by A, right? Now we know when we remove the proportional sign and we get an equal to sign, a constant will come. And here that constant is rho. That is known as resistivity. Either you can write it as this or you can write it as P, right? This is the constant and its name is resistivity. Its name is resistivity. Okay. So it is a constant rho and it's called the constant name is electrical resistivity of the material of the conductor. What will be its unit? So from that equation, that is this equation, if I make rho or P subject of formula, I can write P equals to A will go in multiplication with R and L will come in division. So we know the unit, SI unit of R is ohm. SI unit area is meter square. SI unit of length is meter. Meter cancel. Your unit for electrical resistivity is ohm meter. Right? It is the characteristic property of the material, means it is a property of the material. It depends upon the material, right? It depends upon one more thing, that is it depends upon temperature. So children, resistivity, it is the property of the material and it depends upon the temperature. Now suppose I want to define 1 ohm meter. Suppose I want to define 1 ohm meter, right? So what will the 1 ohm meter? 1 ohm meter is the electrical resistivity when the resistance of the material is 1 ohm and the current is flowing through 1 meter long wire having cross sectional area 1 meter square. So all terms you will define in terms of 1, right? Now let's go to the definition of resistivity of a material. How will you define resistivity of a material? So children, we will take the help of this formula. In this formula, if I take a length of the wire, if I take length of the wire to be 1 meter and I take area as 1 meter square, means I am having length is 1, area is 1. So I am having a cube. I am having a cube whose length is 1 meter square and whose breadth is 1 meter square, area is 1 meter square, right? So it is a cube of side 1 meter. So resistivity will be equal to, if I put here 1, R will be equal to P, that is R is resistance. Resistance is equal to resistivity, right? So resistivity of a material is equal to what? Resistance, right? By 1 cube of material of side 1 meter when current is flowing perpendicularly to the opposite faces. Okay, beta. So this is your resistance definition. Now let's see the difference between resistance and resistivity. Very important. It has come in the exam many a time. So first difference you can write in terms of SI unit. SI unit of resistance is ohm. SI unit of resistivity is ohm meter. Resistance, you know, it depends upon length and area. That is area of cross section of the conductor. But resistivity, it does not depend on length. It does not depend upon the cross section area of the wire of the conductor. Resistance is what? It is a property of conductor to oppose the flow of charge through it. And what is resistivity? Resistivity is the resistance offered by 1 cube of material of side 1 meter when current flows perpendicular to the opposite faces. Then lastly, you can give the formula for R, that is R equals to V by I, and formula for electrical resistivity, that is rho or P, which is equals to R into A by L. So children, this is your difference between resistance and resistivity. So children, let's revise. Resistivity is the electrical resistivity of the material, which is denoted by the symbol rho or P, right? The SI unit of resistance is ohm meter, and it is the property of the material. It depends upon the material, right, beta? So, for example, if you are talking about, if you see this table, in this table, they have listed the electrical resistivity of the conductors of the metals. You will see that the electrical resistivity of the conductors or metals is of the range of 10 to the power minus 6 to 10 to the power minus 8 ohm meter, right? And if you talk about alloys, they are the mixture of two materials, right? They are your alloys. So their conductivity is of the order of 10 to the power minus 6 ohm meter, right, beta? And if you talk about insulators, you can see in the table their electrical resistivity is very large because the insulators, they do not allow the current to pass through them. They oppose a lot, and their electrical resistivity is of the order of plus plus 10 to the power. Their electrical resistivity, that is insulators, is of the order of 10 to the power plus 10 to 10 to the power 17. See, it is plus. They are insulators. They offer a lot of resistance, and so electrical resistivity value is very high. And electrical Resistivity, first thing, it depends upon the material. For different material, you can see the table. The electrical resistivity is different. And secondly, it depends upon the temperature. At high temperature, the electrical resistivity is going to be high. Okay, now let's see some of the applications of this electrical resistivity. So children, alloys, as you can see that their electrical resistivity, it is generally higher than the constituent metals. Their electrical resistivity in the conductors is low, 10 to the power minus 8. But if you combine two materials, two metals, right, then you are getting an alloy. Alloy electrical resistivity is of the order of 10 to the power minus 6. So it is 10 to the power minus 6 is greater than 10 to the power minus 8. So alloys, they are having higher electrical resistivity as compared to their constituent metals. Suppose you compare nichrome, right? If you compare nichrome with the nichrome electrical resistivity with the electrical resistivity of nickel, chromium, manganese, and iron, you can see that its electrical resistivity of nichrome is higher than the individual metals with which it is formed, right? So as its resistivity is high, so at high temperature also, it won't burn. The alloys, they do not get oxidized. They do not burn at high temperature because the resistivity of alloys are higher than their constituent metals. So for this reason, in heating device like electric iron and toaster, alloys are used. Okay, beta. Next, children, tungsten is used for filament of electric bulbs. So it is for the same reason. Tungsten is used for because it is having high electrical resistivity, right? And so what will happen when we pass current through the bulb? The filament, which is made of tungsten, it gets heated, and as its electrical resistivity is high, on passing high current through it, it will get heated, but it will not burn that easily, and it will glow. That is, it will give us light energy. So electrical energy is converted to light energy, right? And moreover, you might have seen that in electrical transmission lines, the wires that are used to transmit the electrical energy, that are generally made of copper and aluminium, because copper and aluminium, their resistivity is high, and so it will send the electrical signals, the electrical power from one point to another without burning down, right? So these are your applications of electrical resistivity. Okay, thank you class. Bye-bye.